She's pointing at me for commentary. I'll say, this man knows what he's talking about.
Good morning, everyone. Today we're going to talk about experiment we did 2 weeks ago in the lab. We had experiment. My name is Ahmed Abkor.
I'm Brent Young.
I'm Mike.
So for this experiment we had 3 objectives. The first one was to study how the flow of compressible fluid is measured by different kinds of meters. The second was to determine how the pressure drop varies with operating pressure. The third one was to study how the temperature affects the measurement of fluid. So a little bit of background about the gas flow in the industry. Gas flow is extremely important in the chemical industry. It's almost present in every chemical process, distillation, absorption, adsorption, gas separation by membranes, you name it. And this is why we are concerning about studying gas flow. So in order to be able to appropriately study gas flow, we want first to measure gas flow, and devices that measure the flow rate of gases or liquids are called flow meters. There are different types of flow meters, having different working mechanisms. For our experience, we use 3 different types of flow meters: water-meters, focus meters, and anemometers. So for water-meters, they are area dependent meter. What does this mean? It means that unlike other flow meters, which depend on the pressure drop, the water meters depends on the change area, as you can see here. The area of the flow meter is changing as we go upward. It also works based on gravity. So as you can see, it consists of a float. This float will move upward if we have a higher flow, or downward if we have a lower float. The float will stop, and there's a mechanical equilibrium between the forces of the fluid and the forces of the gravity until the mechanical equilibrium is reached. Also, the value obtained from the rotometers, which is a flow rate, needs to be corrected to standard condition, and this is the relationship we use here. This is the corrected value, and this is the one obtained from rotometer. We're having the square root here because, as I said, it depends on here. And then we have here the standard pressure and temperature, and the pressure and temperature also at the port. So the second rotometer we use, the Crowley stability voltmeters, consists of 2 oscillating tubes. These tubes will move as the gas moves through them, as you can see here. Gas motion is in place. For then anemometers consist of a propeller and a tail, and the faster the propeller moves, the faster the higher the flow. Also about anemometers, they don't unlike other flow meters which give the flow meter flow rate, they give the velocity. So in order to obtain the flow meter flow rate, we needed to multiply by the cross-sectional area of the anemometer, and also to correct for the readings obtained from the colorless meters and then anemometers, we use the ideal gas law, and this is the flow meter flow rate. So because we wanted to study how the pressure drop varies with operating pressure, here is our theory. According to ideal gas law, with holding all other variables constant and increasing the pressure, the density will increase. So also because we were holding the mass flow rate constant, and the area of the tube was constant, the product of the density and average velocity must have been constant. Then also when we were studying the effective temperature, as you can see, increase in temperature means a decrease in density, which means also a pressure, the viscosity gradient will change. So the runs under was really constant throughout. So this is the experimental setup we had. The flow of air starts from here, goes all the way until it reaches the first 1 meters, which can be seen over here, and then goes all the way until it reaches the second 1 meter or 1 meter, which is here. Then it goes to the lowest meter, nanometer to the atmosphere. This is the regulator top pressure, where the pressure was being adjusted. And this is the gauge, the pressure gauge, which when we took when we take our operating pressure function. Then we have two pressure gauges here, one at each millimeter. Now, Brent will enlighten you about our results.
So we divided our experiment up into 3 different sections in accordance with our 3 objectives. And so the first one was to kind of standardize and calibrate and see how the different flow meters in different parts of the experiment were working. And so we got pretty consistent results throughout, especially at lower pressures. And so they all gave about the same readings. But as we increased the pressure, we started seeing a variation in our readings. And so there's two groups. One are the rotameters, and those are very accurate because we took the pressure from the pressure gauges right at the rotameters. We know where those are. However, for the Coriolis meter and for the anemometer, we didn't have exact pressures for those locations. So in our calculations, we used the pressure at rotameter 2. However, there is a pressure drop between the pressure gauge for rotameter 2 and the Coriolis and the anemometers. We could kind of guess about that pressure drop, but in the end, we would just be force-fitting our data to fit the other ones. So we can kind of show that it's about the same. Those numbers should be lower due to a pressure drop that we can't account for. So we're able to show that correcting for standard conditions throughout the system, that we can get the same readings coming out of it. Next slide. So as we picked 3 different mass flow rates, and we started running different trials at different operating pressures. And the first thing that we noticed that as we increased our pressure, we increased our density as well. This follows mathematically. It fits pretty perfectly. It's a linear relationship. And so then we started seeing what happened when that density increased. Next slide. So as we increased our density, our velocity decreased. This is in accordance with what we expected to see, in accordance with the math as well. As we increased our density, our velocity is going to decrease. And it happened almost linear, but not quite. Next slide. This is really the most important part, is that as we increased our density by increasing our pressure, decreasing our velocity, we decreased our pressure drop. This happened, so as we increase operating pressure, our pressure drop is going down for all flow rates. So next slide. Why is this happening? This happens because if we look at it with velocity instead of with pressure drop, as we increase our velocity, we increase our pressure drop. So it makes sense that if we're taking a given volume or a given mass of material, and then we're compressing it down, or maintaining the same mass flow rate, we have to move through slower in order to get the same mass flow rate. Or as our velocity decreases, our pressure drop is decreasing as well. And this happens because the pressure drop is directly proportional to the shear stress that's on the walls of the pipes. So as we're moving by the walls slower, there's less shear stress, which means that we're going to be decreasing our pressure. A little bit later on, we're going to talk about why this is important. But in order to make sure that all of our values were good, we had to ensure that we're a fully developed flow. Using this equation right here, we determined that we needed about 1 foot in order to make sure that we got to a fully developed flow. And there were many 1 foot sections before we got to any of our readings to ensure that we were actually a fully developed flow. So after we went through and calculated all our data, we were able to calculate the friction factor, or the fanning friction factor, for the experimental setup. We were able to find pretty consistent results. It's pretty flat at these high Reynolds numbers like you would expect. The variation was about 0.0005. But it is much less than the expected friction factor that we would have gotten from the Moody chart. And so ways that we were kind of wondering about this might be from the fact that our pipes are a little bit smoother than the expected roughness of Schedule 40 stainless steel pipe, which is 0.00165. Our experimental setup might be a little smoother than that, leading to a lower friction factor, and as well as just kind of uncertainty about our Reynolds number might have led to some different calculations for this. Next slide. Our last part of the experiment was evaluating the temperature effect of what would happen. There was a heater in the line. We turned it on and ran to 70 degrees Celsius, which is about 158 degrees Fahrenheit, and then seeing how that changed the readings on our flow meters. So for rotameter 1, it was before the heater. So after we turned on the heater, it was exactly the same, which is exactly what we wanted to see. There was no kind of weird feedback system in the experiment. So rotameter 1 is good. When we start looking at rotameter 2, we get an interesting kind of reading, is that our standard cubic feet per minute is going up, but the mass flow rate is constant. This is within our experimental error after we correct it back down to standard conditions, which is to be expected. We don't want to see more mass all of a sudden flowing through as soon as we heat it up. So correcting the standard conditions, we get a result that's identical, but when it's within experimental error. The most important part that we see here is the anemometer, which is increasing. We're getting more mass or more velocity going through the system. This makes sense when we look at it in terms of the density. As we increase our temperature, we are decreasing our density, which causes the mass to expand, but it can't expand because it's in a fixed area, so it has to start going through faster. This is what the anemometer shows us. The Coriolis meter also gives us very interesting readings. For some reason, it decides to go down. And when we were contemplating and looking into this, we realized that it could have been, there's additional kinds of pressure drops, there could be additional temperature drops that we aren't able to account for when it gets to the Coriolis meter because there's no temperature reading there. But one of the main reasons that we kind of realized is that due to the nature of the oscillating tubes of the Coriolis meter, they're highly dependent on the material properties of the meter. And one of those is the stiffness of those oscillating tubes. So as we increase the temperature, we are decreasing the stiffness, which decreases our mass flow rate. And so that explains the difference in readings from the Coriolis meter. So in conclusion, we've got a bunch of different types of flow meters, and they're going to be all over any kind of plant or any kind of project experiment that you work on. And it's going to be important to realize to take readings of the conditions at those places and then correct them to standard conditions so that you can compare readings from different places. And it's pretty easy to do. You've got correction factors for rotameters, which you utilize a square root function, and then you also just have the ideal gas law for a lot of other ones. But the most important thing that we can learn is that as pressure increases for a given mass flow rate in a cross-sectional area, the pressure drop decreases. This saves you money because when you're talking about moving a lot of material, say a natural gas pipeline coming out of Alaska, you're going to want to run it at very high pressures to minimize that pressure drop so you don't have to add compressors every mile, every 2 miles, which is why natural gas pipelines are generally run in excess of 100 bar, and your compressors are set up to bring it from 100 bar up to about 140 bar, and then when you drop back down to 100 bar for your pressure drop to bring it back up again. So that's the most important thing to learn from our experiment. Then the last one is that as the temperature increases with holding your mass flow rate in your area and the pressure constant, the volumetric flow rate increases. And so this just happens because of your decreasing density, you have this constrained area, which means that your velocity is necessarily going to increase and your volumetric flow rate increases as well. So this concludes our presentation. Thank you very much. Do you have any questions?
All right, we have questions for them?
Mr. Thompson?
I'm speechless.
So, if you go back to the one that directed discussion. So, let me understand this. So that I understand that if you had a higher pressure, you have a lower pressure drop.
Yes, sir.
And pressure drop does cost you money. But so does getting into the high pressure in the first place. So,
Assume we have very cheap.
but if you had a cheap compressor, then pressure drop wouldn't cost you money. I'm just confused about, and there may be other reasons why they wanted a high pressure. Or you may need a high pressure to make it all the way wherever it's going, right? But trying to decrease costs results on high pressure. Yeah.
This is general. Maybe just decreasing it in the first place instead of just adding to the reservoir.
Yeah, I mean, I think certainly understanding what's going on is important. I'm not sure that we've got the right conclusion. You might, I don't know, unless you read it somewhere.
Yeah, well, it's obviously just about optimization, so it's having the flexibility to optimize with the number of compressors you have. And those compressors. That's kind of what that's about.
Yeah. Okay, then if we go back to the one about the frequency factor, so that one, so, the plot is a movie chart.
Yeah, it's just celebration factor.
So hopefully it doesn't seem like it's a question. You said earlier the rental is constant from the experiments, but you did it at different.
Yeah, so to answer this question, Reynolds number is constant at the same mass flow rate. However, when we increase the mass flow rate, Reynolds number increases because since we have a constant cross-sectional area, the only thing will increase the velocity. So mass velocity is increasing with increasing mass flow rate. That's why Reynolds number is increasing. The other interesting fact here is the huge increase in the Reynolds number is not reflected in the experimental friction factor, and that's an interesting fact about the chart. As we have higher Reynolds number, the friction factor is going to be almost constant.
Right. So then, the expected is around 0.6, like you said. The expected over here in this last column is the blue line, right? So yours,
The experimental.
so the expected.
The expected. Theoretical.
Yeah, that's the blue line.
No, the experimental is the blue line.
Oh.
They
Yeah.
didn't have it on the blog.
Oh, okay.
Yeah.
No. Because your experimental goes 04, and the blue line is up around 06. Okay. That's what I'm confused. I thought you said that
No, it goes to this number because we are. I think we are rounding. We round here and the uncertainty also. We accounted for the uncertainty in the plot.
well, I mean, there's nothing at 0.004 on the graph.
You're saying that the movie graph is the expected.
Oh yeah, so the expected.
Yeah, that's the expected.
Yeah,
So your
that's the
data,
expected.
so it would be
Yeah.
nice to put points where your actual experiment.
Sure. Yeah.
Usually that's what we do, right? But the expected is
Yeah.
okay. So if you did put the points, they would be lower.
Yeah. The experiment.
But they had sort of the same trend, they dropped.
Yeah.
Yeah, the pressure drop was about, or not the pressure drop, the drop was about 0.0005
Okay.
for both of them.
Yeah.
So you got the clear on that. So then, and I'm just asking more or less to repeat what you said already. Why were they different? Which your experiments were lower.
Yeah, because we think that.
I mean, their experimental were lower.
Yeah, we expect that the later process we have, our pipe in the lab was more smooth than this later process. So that's why we have smaller friction.
Okay. Any other questions?
How do you spell relief?
Yeah, that's where they started wrong in the presentation. I was like, where did you put that?